Telescope collimation, which is a needlessly big word, which just means alignment. In the case of refractors, they are collimated at the factory. The objective lenses are aligned to point straight down the optical tube assembly to the eyepiece. In the case of Newtonian reflectors, like this one, they're not. Newtonian reflectors have two mirrors. A big mirror here in the back called the primary mirror, and a small mirror up here in the front called the secondary mirror. Light comes in through the front, goes to the back, hits the primary mirror, is reflected back up to the front where it hits the secondary mirror, and then goes up through the focusing tube to the eyepiece. Collimating the Newtonian telescope simply means aligning those two mirrors. In the back, you'll see there are three sets of screws. Now, in some telescopes, they're all thumb screws, usually look different. This particular telescope, the collimating screw is a thumb screw, and the lockdown screw next to it is a Phillips head. Each telescope will have different combination of those. To collimate them, the primary mirror, you loosen the lockdown screws, which are holding the primary mirror in. And then you adjust the collimating screws, which angle where the mirror points. The objective of that is to get the primary mirror to point precisely to the center of the secondary mirror. The secondary mirror has screws up here in the front, three of them, and you adjust those to get the secondary mirror pointing exactly to the primary mirror. Once those are pointing precisely to the center of each other, the mirrors are aligned and the telescope will work. Now, if we take the metal tube away, what we end up with is two mirrors. This is the primary mirror. I don't know if you can see that. You can see your face in it. You'll see your face looks a little bigger. This is an awful lot like a makeup mirror. It's concave. This particular one has a center point, which is kind of important. There are three clips on the mirror. They're called the mirror clips. The lockdown screws in the back work with these mirror clips to hold the mirror in. Takes the mirror clips off, and the primary mirror will just fall out of the telescope. This is a secondary mirror. It's a flat mirror set at a 45-degree angle. It's held in by these four vanes. In some scopes it's three. Some scopes you only have one or two, but they're called the spider vanes, and their job is to hold the secondary mirror assembly in the telescope so it doesn't just fall out. If you look careful, you might be able to see there are screws. Here's where the screws start off. When you adjust these, when you unscrew them or screw them in, those screws move this around. So the whole point is, light comes in, goes back, hits the primary mirror, is reflected forward, or it hits the secondary mirror, ricochets off the secondary mirror up through the focusing tube into the eyepiece. Sir Isaac Newton, the fellow who invented physics, had an interest in astronomy and optics and the like, and back when he was in the early 1600s, about the only kind of refractors, refraction, by the way, just another big word, means bending. Refractors bend the light. kind of like a prism. And like a prism, they produce false color. I mean, you got the spectrum, the colors separate. Lenses do the same thing. And back when he was doing his astronomy, they only had singlets. They'd have a single lens, poorly made, and it would throw all kinds of rainbow false colors. He didn't like that. So he figured, well, why should I bend the light if I can simply reflect it? So he invented the Newtonian reflector. It's not glued in place like the refractors usually are, because for one thing, you have to take the back of the telescope off to clean the mirror. You can't reach your arm all the way down there to clean the mirror when it gets dirty. And when you put the mirror back on, it's not exactly in the same, down to the millimeter, in the same spot that it was when you took it out. So you have to readjust the mirrors. And that's how Newtonian reflectors work. Today I'm going to make a little short video about how to collimate or align the mirrors in a Newtonian telescope using this. It's called a laser collimator. It shines a little laser beam down, bounces off the mirrors and stuff, and you look and see where the laser is and adjust with the collimation screws on the back or the collimation screws in the front and align the mirrors. It's not all that difficult and doesn't take that long. Each one of the mirrors in the front are going to have slightly different tools required. I'm going to be doing an Orion space probe, 130 millimeter. And to adjust these screws in the front, I'm going to use this, a 2 millimeter Allen wrench. Some telescopes will use the 2 or 3 or 4 millimeters. Some will have Phillips head screws. Some might have knobs, like bob knobs, so you just turn it with your fingers. So you have to look at your telescope or look at the owner's manual to find out which one you're going to use. With the laser collimator, it says 0 here, that's off, all the way up to 7. So you can adjust the brightness. I normally go with a 3 or a 4, depending on how much light there is in the room. If I'm outside in the dark at night, I can actually do it with a 1 or 2. I'm going to turn it to a 7 here because I got some pretty bright lights shining in my face. And it'll be hard to see a 1 or a 2. So you adjust it by turning this thing. Now once you've done that, don't look at the laser. I'm going to shine at the camera. That's the laser beam, and you'll be able to see it on the primary mirror. And we're going to adjust the secondary mirror with this Allen wrench to make the secondary mirror point to the middle of the primary mirror in that little circle I showed you. Oh, when we put this on, we're going to take this open place here and face it toward the rear of the telescope, because later on we'll be using that and it'll need to face the rear. So we put that in there. We face this toward the camera. Adjust the camera. You won't have to do this unless you're filming it. But since I am filming it, I have to adjust the camera and get it pointing to a different place than it was when I was talking. Aha! There's the telescope. All right, if you can see that, the center dot is right next to the laser pointer. So it's not badly out of alignment. So what I'll do is I'll take this, I'll stick it in one of these screws, and I'll pick a different screw because that one didn't work well. There. The laser pointer is now in the center of the primary mirror. So the secondary mirror has been collimated or adjusted. To adjust the primary mirror, we then flip it around, and I move the camera again. Alright, you should be able to see the laser dot right there. This side's badly out of collimation. We'll have to move this laser dot down to the center of the aiming reticle so that it's behind that black dot in the middle. That black dot in the middle is the secondary mirror. So once the laser is behind that black dot, the primary mirror will be collimated. I'll do that after I adjust the camera. I'll do that by turning these things. And there, it's now behind that black dot, so the primary mirror is now collimated. Now, before I started this, I loosened the lockdown screws. You'll need to tighten the lockdown screws after you've collimated it. You have to be real careful when you're moving these lockdown screws to just move a little bit at a time, because while the mirror is still loose, if you pull a lockdown screw too much, that will ruin the collimation. And I normally do these till I meet resistance. I do a little bit at a time until I got them all thumb tight. Or if they have Phillips head screws for the lockdown screws, I just do it till they're snug. And that's how you collimate a telescope with a laser collimator. And I adjust this thing, put it back out a little bit so you can see my well-lit face. You don't have to collimate the mirrors every time you use the telescope. I always check before I use the telescope to see if it needs collimating. But if you are handling it roughly, or if you throw it in the trunk and go out to a dark site and it's bouncing along all the way out there, you'll no doubt need to collimate it. Or if you throw it end over end down a long stone stairway, you'll definitely have to collimate it. I usually lay mine on the floor on the side so that I don't lay it on with either end up and down. I lay it laterally. And I don't have to collimate them all that often. A couple points about laser collimators. Laser collimators may need to be collimated themselves. There's these little holes. There's 3 of them. They're currently covered up with a little bit of cloth. You can poke through that with an Allen wrench and adjust them. Mine was collimated when I got it, and I haven't had to collimate it since then. If you want to check the collimation, you stick it in the focusing tube, turn it on, look at the mirror here in the front, and it should be pointing toward the center, then rotate it. And if as the laser turns, it stays in or very near the center, you're okay. But if it's making wild turns around, means this needs to be collimated in order to get accurate collimation. The last warning about these, I did 200 or 300, I've got 7 Newtonian reflectors. I did 200 or 300 collimations before I found out you're not supposed to look at a laser or the reflection of the laser because it can blind you. Now I have an Astromania. I looked it up. Astromania is supposed to be well within safe limits when they make it at the factory. I guess if you did this on 7 maximum gain and it had been messed up at the factory, it might put out enough heat and light to damage your eye. But although I've seen a bunch of warnings when I was reading or watching videos on collimation, I'd never had a problem with it. But I'm not going to tell you to look at a laser, so never, ever, ever use this because you'll blind yourself. Yeah, that's all there is to it. So, till I see you again, happy trails.